Hello there, Mr. Sutton with the BC Calculus 8-4 Extra Practice number 3 solutions on vector free response practice. For this calculator-based free response problem, we have an object moving in the xy plane, defined parametrically with x of t and y of t. They didn't tell us what those were, but they did tell us the derivatives of those. So we essentially have the components of the velocity for this particle. And let's see, we have an interval from 0 to 3. We have a time 2 at which we're at the position 4, 5. All important stuff. Now for our first part on this problem, we want the equation of the tangent line at 4, 5. So for tangent lines, we need an x value, a y value, which they provided here, and the slope. dy over dx, per a parametric here, is going to be a y prime over x prime. Now specifically, at time 2 here. They want the line tangent to the curve at 4, 5. So that means there's this time 2 that's kind of in the background. So I'm going to do then y prime of 2 divided by x prime of 2 to find that slope at time 2. And for that, I will use the calculator. To make things go a little more smoothly, I'm going to go ahead and put dx over dt, x prime as my y1, and y prime as my y2 on the calculator. And now let me do this stuff here. Let me quit out to the main screen. Fancy fraction. Let me do y prime of 2, so that's going to be alpha trace y2 here, and we're plugging 2 into that. And down below, I need x prime of 2, so that's going to be alpha trace y1. That's where I stored x prime. Plug 2 into that. Press enter and hope for the best. Oops, let me plug 2 in. There we go. All right. So that comes out to about 15.604. Now we actually have to write the equation of the tangent line. So I'm going to have y minus the y value 5. So I'm going to use point slope here. And then that's going to equal my slope of 15.604 times x minus the x value 4. For this part of the problem, I need the speed of the object at time 2. So all I have to do on this one is just square root of x prime of 2 squared plus y prime of 2 squared, standard speed setup here. For that, I will need the calculator. Here's what it looks like on the calculator. Now remember, I stored x prime and y prime as y2 or y1 and y2 on my calculator. So I'm just plugging 2 into those directly and squaring the outputs from those. And square root of all that gives me 2.275. For part C, I want the total distance traveled by the object from 0 to 1 for the time. So for this, I essentially just need to integrate speed over the interval 0 to 1. So I have the integral from 0 to 1 of square root of x prime of t squared plus y prime of t squared, all of that with a dt after. Back to the calculator. Here's the setup for that integral on my calculator, 0 to 1. And then we just have y1 squared plus y2 squared inside that square root, dx. Enter. Comes out to about 1.458. For this last piece of the problem, they want the position of our object at time 3. And now it's crucial here that they told us these differential equations applied between times 0 and 3. So that means we can actually use them to help us out with this. So I'm going to have to use the FTC on this one. I need the initial value of x, which is 4. So if I'm doing x of 3, I need 4, plus the integral from, let's see here, time 2 to time 3, so from 2 to 3, of x prime of t dt. Let me do that on the calculator. So here it is, 4 plus integral 2 to 3. y1, again, is where I stored x prime on the calculator. dx, that comes out to about 3.953, actually 954 if we round up. I guess you could truncate too, either way. So now let's find y of 3. That's going to be my initial y value of 5, the y of 2 value there, plus the integral from 2 to 3 of y prime of t dt. And back on the calculator, I only need to change a few things from what I did with x, so I'm actually just going to arrow up and steal the input from before and then just modify a few things. For example, this 4 over here should now be a 5. So let me make that a 5. y1 should now be y2 because I stored y prime in y2. So alpha trace y2, there we go. But everything else is the same, integral, dx, everything else. So that comes out to about 4.906. Putting it all together to write an actual point, we have 3.954, comma 4.906. On this calculator-based free response, we have an object moving on a curve in the xy plane with this parametric definition for its position, and we have x prime given to us, y prime dy over dt they didn't give us. At time 2, they're telling us we're at 1, 8 for a location. So we want to find, for the first part here, the x-coordinate of our position at time 4. Okay, well, let me go ahead and set this up, and then I'll use the calculator to help me out. So we essentially need to use the fundamental theorem here. We have an initial x value of 1. If I want to know x of 4, I need to take that 1 and add to it the total change between times 2 and 4. So the integral from 2 to 4 of x prime of t dt. Let me use the calculator now. Now, one thing I am going to do before I even run these numbers to set myself up for success here, I'm going to put my dx over dt in as y1 so I don't have to keep rewriting it. And then quitting out of that, let me do 1 plus math 9, so integral from 2 to 4 of, now I can do alpha trace y1 and dx. All of this is going to come out to 7.133. On this problem part, they're telling us at time 2, value of dy over dt is -7. They want the equation of the tangent line at the point x of 2, comma y of 2. Okay, so for tangent line, we need an x value, a y value, and a slope. We actually have the x and the y value. They said up here at time 2, the object is at position 1, 8. So that is the x and the y value we need. For the slope, though, we need our parametric dy over dx formula. That's y prime of 2 over x prime of 2 in this case. And to help myself out, I'm going to explicitly spell out the fact that y prime of 2 equals -7. I'm not really sure if this is enough for them to look at y prime of 2 and just know that it's -7, so I'm going to spell it out just to be on the safe side. All right, so my derivative then at 2 is going to be y prime of 2 over x prime of 2. And now that's just going to be -7 over whatever I get when I plug 2 into this x prime up here. So I am going to need the calculator. So on my calculator, here's what this looks like. X prime of 2, again, that's going to be y1 of 2 because I stored x prime in y1. Y prime of 2, we said that was -7, so I'm going to enter that directly. Pressing enter now, it's about -2.983. And then they want the equation of the tangent line, so we're not done yet. So I have y minus the y value 8 equals my slope of -2.983 times x minus the x value 1. Now I'm done. For this part of the problem, I want the speed of the object at time 2. So in general, I'm going to need the square root of x prime of 2 squared plus y prime of 2 squared. Now x prime of 2, I can again get that on my calculator using this dx over dt function I entered. Y prime of 2, again, they told us that had a value of -7 back in part B, so I'll use -7 for that. So here is what I'm actually entering in the calculator. We have square root of, and then again, x prime of 2, that's y1 of 2, square that, plus -7 squared. All of this comes out to about 7.383. For this last part of the problem, we have, for time greater than or equal to 3, the line tangent to our curve has a slope of 2t plus 1. Okay. And they want the acceleration vector of our object at time 4. So acceleration vector, we need x double prime and y double prime of the input, the time, of 4. That's not an issue for x double prime of 4 because we already know x prime right here. So I can take the derivative of a function they've already defined at 4 and not have to do any other further work. Just plug it in my calculator. Y double prime of 4 is an issue because we actually don't have y prime at all. So I can't just write y double prime of 4. I don't even know what it does. So that's where we use this information about our slope being 2t plus 1. After time greater than or equal to 3, I can write that dy over dx which is equivalent to y prime of t over x prime of t, I can say that this has a value of 2t plus 1. Now the reason this is good news is because I actually already know what x prime of t is. It's this function up here. So if I just multiply both sides by x prime of t, like so, I now have a legitimate function I can use for y prime of t. I know how to plug 2t plus 1 in my calculator. X prime, I've already got that in there as y1, so I'm good to go. So my acceleration vector then, I'm going to have x double prime of 4, comma y double prime of 4. And now let me find both of these on the calculator. Before I do any actual plugging in though, I'm going to take the time to define y prime of t. So remember, that was going to be 2t plus 1 times x prime. So what I'll write here is 2x plus 1. And then I'll multiply that by, let's see, alpha trace y1. This function up here, because, I mean, why rewrite it if I don't have to? All right, let me quit out of there now. And to get x double prime of 4, I need the derivative of x prime at 4. So math 8 derivative. We have a dx alpha trace y1. And then we're plugging in 4 for that, giving me a value of about 2.303. So we'll put that down there. Now for y double prime of 4, I'm going to do really the same exact stuff, but I'm going to use y2 instead of y1 because now I want y prime. And my calculator does all the other heavy lifting for me. So alpha trace y2, enter, comes out to 24.814. On this calculator-based problem, we have a diver leaping from the edge of a diving platform. Very nice stick figure there. The figure above here shows our initial position, and we have the horizontal distance from the diving board as x of t, and the distance between the diver's shoulders and the water level is y of t. Here's the change in x, here's the change in y, and our shoulders are starting 11.4 meters above the water when we make the leap. Okay, so given all this information, and this all applies between 0 and a, where a is the time the shoulders hit the water. Obviously, none of this is going to hold true after we hit the water. So first task, we want to find the maximum vertical distance from the water to the shoulders. I'm just going to take a moment to enter these as my y equals in my calculator. Now, it may not seem like there's a huge gain putting, for example, 0.8 in as a function, but I like to think a little bit more abstractly about all this kind of stuff, so hey, it helps me. Okay, so finding that maximum vertical distance, we need to take the derivative of y, which y was our vertical distance, so take its derivative, y prime, and look for critical values. So I'll start by seeing where this expression takes on a value of 0. And I could probably do this without a calculator, but I'm going to use the calculator anyway. Why not? So back in my y equals, I'm going to deselect the y1 there because that's x prime. I don't really care about that right now. It's just y prime. And I don't really know exactly when we're hitting the water, but I mean, it can't be more than a few seconds. Let me just do zoom 4 and see what that gets me. So yeah, we're changing our derivative. We're crossing the x-axis pretty quickly there. Let me do second trace option 2. And then for my left bound, we'll go there. For my right bound, we'll go a little bit below, enter again. And that is going to be where we're crossing here, about 0.3673 seconds. I'm going to go ahead and store that as P. So that's what P represents. And let me do that immediately on my calculator as well. So quit out, and then store, and then we'll do alpha P. All right. Now coming back here, I need to show that this is where the max actually happens. So this is the only critical value on this graph. I can say that y prime is greater than 0 between 0 and p, and y prime is less than 0, so y is decreasing from t greater than p. So therefore, the max vertical distance happens at time equals p seconds. Okay, so we also want to figure out what the maximum vertical distance actually is, And to do that, we have to do a little more calculus here. We need to basically plug p into the y function. The trouble is we don't have a y function. We have a y prime, though, so we can use fundamental theorem to help us out with this. I can say y of, let's see here, this would be y of p. That's going to be my initial value of 11.4 for y, plus the integral from, let's see here, that was at time 0, so 0 to p seconds, integral of y prime of t dt. And let me go back to the calculator for this. So we've got 11.4, and we're adding, let's see, math 9, integral from 0 to, now I'm really glad I stored this as p or whatever letter you wanted to use. And y1, I stored that as, let's see, alpha trace y2, that was my y prime. And then dx, all of that comes out to about 12.061. And that's going to be in, what was our units on this one? Meters. There we go. For this next part of the problem, they want us to actually find A, the time when the diver's shoulders enter the water. So in order to do this, we need to set up an expression for A, or for y of A, because we know that when we reach y of A, the vertical distance at time A, that should be 0. So y of A, we can use our FTC again. We can say that's our initial value of 11.4 plus the integral from 0 to time A of y prime of t dt. And we know that if we pick the correct A value in this situation, that should end up being a position, a distance of 0. So this is something we can actually plug into our calculator and solve. To do this on the calculator, I'm going to go into my y equals in y3, and I'm going to set up basically an integral kind of function here. So I've got my initial value of 11.4 plus, now I'm going to do math 9, and we're going from 0 to, we'll call this x here because that's what your calculator expects for the input. Now in here I'm taking y prime, so that would be alpha trace y2. And it turns out it doesn't really matter what you use for this d over here. I'm just going to use x. Normally you shouldn't have the same variable here and up here, but your calculator doesn't really seem to care, so we do it anyway. I'm also going to make sure I deselect my y prime up here because I don't want to graph that again. And again, I'm not really sure when this is going to happen. That's kind of what we're solving for here. So let me just put in, let me just do, I don't know, zoom 4 again and hope for the best. Actually, here's what I can do. Let me just stop this. Let me make my window, let's go from, obviously we don't need negative time, so let's go from 0 to 4.7 and zoom fit this thing. All right, so zoom 0. Let's see what happens now. And it's taking a while to think about this because we're asking it to do a fair amount here. These integral functions do take a while to graph. But here's what we come up with. So here's the diver, and we're diving, and we're diving. We're picking up speed. This is our vertical position now, and there is where we cross the water. Okay, and apparently this happens a little bit less than 2 seconds, so we're taking a while to graph the rest of this out. Unfortunately, you do have to wait for the rest of this to graph if you want to go back and actually be able to find the intersection. So time passes, get a book, whatever. All right, so now we'll do second trace, zeros, and we're going to do a little bit to the left, a little bit to the right, enter again, and this gives us the value of, it's even taking a while to think about that, about 1.936. So that happens in 1.936 seconds. And almost forgot, but one thing I am going to do while I'm on this part of the problem, I might as well go ahead and actually store that value as A in my calculator. I almost forgot because they were already calling this A all along, but let me go ahead, quit out of there, and let's do store alpha A. There we go. Now if I need to use that again, I can. On this part of the problem, we want the total distance traveled by the diver's shoulders, which is kind of a weird way to phrase it, from the time she leaps until the time she enters the water. So we're asking for basically the integral of speed on this one if we're asking for total distance in kind of a two-dimensional space. So I'm going to need an integral from 0, the time she jumps, to a, the time she lands. And then I need to take the square root of, we're going to need x prime of t squared plus y prime of t squared with a dt. Let me plug that in the calculator. So we have, let's see here, we already stored my value from part B as a. So now I do math 9, and we're going from 0 to alpha a. And then this is going to be, let's see, square root of, we've got alpha trace y1 squared. This is where it was nice that I stored something as y1, so now I don't have to actually remember what it was. I just know this is x prime, plus alpha trace y2, and we'll square that as well. And put a little dx out here. Enter. And this is going to give us about 12.946 meters. For this last part of the problem, they want the angle between the path of the diver and the water the instant our shoulders enter the water. So for this one, the key is taking a look at what you've got and what you need. We've got stuff about x and y values up here. We need something about an angle. Well, if you want to get an angle out of x and y values, then you're going to need to use the tan function. Specifically, if you want the angle of entrance, you need to figure out the slope at which we are entering the water and basically take the inverse tan of that slope at time a. Okay, so how do we get the slope? Well, we've defined this function parametrically, so the derivative is just going to be y prime over x prime at time a. So y prime of a over x prime of a. We can do that on the calculator. So here's what that looks like on the calculator. Y prime was y2. X prime was entered as y1. We're plugging a into both, even though x prime really doesn't care. So let's press enter. Comes out to about negative 19.219. I'm going to go ahead and just store that as a variable. So I'll store that as, I don't know, q, whatever. Doesn't really matter. But now I can refer back to it. So now to get the actual angle, I've got a slope here. To get the angle out of this, I need the absolute value of the inverse tan of this. And I say absolute value because, I mean, you have a downward slope, but they wanted a positive angle here. So we're just going to consider this as like a positive slope to get a positive number just to make them happy. So we'll do the absolute value of tan inverse of q. And going back to the calculator, let me do, let's see, alpha window to get absolute value. And then we need tan inverse, so second tan and q. Alpha q, there we go. Close that parentheses. And all of that is coming out to about 1.519, which is somewhere between 0 and pi over 2. Pi over 2 is about 1.7 and change.